Hello, so this is your new lesson about matrices. A matrix can be seen as a table of numbers, but if you want, you can see it as several vectors. So you have a first vectors which coordinates are 1 and 3 here, and a second vectors which coordinates are 2 and say 0, for example. And this is going to be a matrix. These coefficients, if this matrix is called A, the coefficients are called A with I and J, and I is the number of the line or the row, and J is the number of the column. Remember that the row is always first and the column is always second. We have several matrices that have specific properties. For example, a row matrix is going to be a matrix with only one row, one line, and it's called a line vector too, which means the dimension here, the number of lines is 1 and the number of columns can be anything. This is a column matrix. You have one column and several lines or several rows. These two types of matrices represent vectors. A square matrix is a matrix with as many rows as it has columns, like 2 rows, 2 columns. Most of the matrices are not that way. They are like with a random number of lines and a random number of columns, like this one, for example. Zero matrix is a matrix with all of its coefficients equal to 0. A diagonal matrix is going to be a diagonal like that, and except on the diagonal, all the coefficients will be equal to 0. Identity matrix is a matrix, we'll see why it's called identity. And this one is called I, and sometimes you add 3, which is the number of lines and columns. The set of the matrices that have, like, for example, 3 lines and 3 columns, which means they are square matrices, is called M3. But if you have, like, for example, here, 2 lines and 3 columns, this set is called M23. We'll say that 2 matrices are equal if they have the same coefficients. So now you should do the first exercises, which are about the coefficients. When adding 2 matrices, they have to be the same size because otherwise you can't add them. Be careful because with matrices, not all operations are possible. If you want to add 2 matrices, I'm choosing random numbers, but I'm making the 2 matrices the same size. You will add this coefficient with this one, this coefficient with this one, and so on. 5 plus 6, and here 2 plus 1, and here 4 plus 5, and here 1 plus 1. So your result will be that matrix, this one, okay? Same thing for subtracting matrices. Of course, if you add the 0 matrix, you'll get the same matrix as you had first, as you had before. 0 stays neutral for addition. if you want to multiply a matrix by a number, like for example, 5 times A, I'm taking this matrix A. 5A means that you are simply multiplying every coefficient in the matrix A by 5, which means your final result is going to be 5, 15, 10, and 0. This is just a quick overview. So if you want more specific, if you want more precisions, I gave you the URL of another video. Of course, if you want to multiply A by 2, then 3, it's the same thing as multiplying A by 6. The opposite of a matrix is going to be the matrix which coefficients are opposite from the first one, like the opposite of A is this. And you have the same priority rules between operations as in the numbers. Now let's talk about multiplying matrices. It's slightly more difficult. If you want to multiply, first we'll see how it works with a row vector, which is a line vector, times a column vector. How you will multiply those two vectors or two matrices is you will multiply this by this. 1 times 2 is 2. 2 times 3 is 6 plus 6. Let's take a negative number here and here. Minus 5 times 0 is 0. Minus 4 times 1 is minus 4. So you'll get a number here. 6 and 2 is 8. Minus 4 is 4. So what you are doing is, if this is vector u and this is vector v, what you are computing here is the dot product between u and v. This is how you multiply row matrices by column matrices. Now, if you want to multiply in the general situation, two matrices, like for example, I'll take an intermediate example. So I'm multiplying a square matrix. So this is where I put the first term of my multiplication, and this is the second. This is A times B. This is matrix A, this is matrix B. If I want to multiply these, I'll do the same. 5 times 2 is 10, plus minus 1 times 2 is 2. 3 times 5 is 15, plus here you'll get 0. So your result is going to be 12 and 15. This is a column matrix or a column vector. Now, if I want to multiply two matrices, two square matrices, for example, but you can multiply matrices that are not square. 1, 0, minus 3, minus 2. I'll multiply this times this, so I'll get minus 4, and this times this. So when I multiply this line times this column, I'll get this number here. So this is minus 2 times, this was minus 6, I'm sorry. Oh, I don't see it anymore. Minus 6 times minus 3, I get plus 18. Here, 2 times 1 is 2, and minus 2 times minus 3 is 6. Here, to get this number, I'll see where this line crosses this column. So minus 4 times 0 is 0. Minus 6 times minus 2 is 12. And here 2 times 0 is 0. 2 and minus 2 times minus 2 is 4. So what I'm getting is 14, 12, 8, and 4. So if this is A, matrix A, this is matrix B, this is matrix A times B. Be careful, because in general, the product of two matrices is not commutative, which means A times B will not get you the same results as B times A. Of course, you can multiply two matrices that are not square matrices. For example, this one can be multiplied by, as long as you have as many columns here as you have lines here, so you can do this. The multiplication is possible. It doesn't mean you'll get an interesting result, but it is possible, okay? And sometimes if you don't have the same number of rows of columns here as you have the number of rows here, the multiplication is simply not possible. So here is an operation which is not commutative and not always possible. That's very different from the number situation. Now, what you call the inverse of a matrix. Be careful, because not all matrices are invertible. The inverse of A will be denoted A to the power of -1, which means, and the definition of that matrix is the matrix such that this matrix times A is equal to A times this matrix is equal to the identity matrix, which means you always have to check that these two products are equal to identity, because it is not commutative. So it's not because you had this one equal to identity that this one will be equal to identity. In that case, your matrix is invertible and its inverse is A to the power of -1. So I gave you several exercises about that. Your calculator can compute the inverse of a matrix. So this might be very helpful. Now you have all the ordinary properties of a product. Like if it's associative, it means if you compute A times B and then times C, it's the same result as computing B times C and then multiplying by A. Be careful, because as it is not commutative, when you multiply by A on the left, you won't get the same result as when you multiply by A on the right. Another classic property is that multiplication is distributive on addition, which means, as usual, you can do that AB plus AC and so on, and all the usual properties, except it is not commutative. I know I'm repeating myself, but it's very, very important. Now, if you want to know if a matrix is invertible, you will have to compute its determinant. So the determinant, I've already presented the determinant in the vectors lesson. So if I have a matrix A, which is, for example, I'm looking for a good example, but I don't have any, so okay. Let's take A, 1, 2, -1, 0. The determinant of this matrix is between bars and not parentheses. And you computed that by multiplying this by this minus this times this. So your determinant is 1 times 0, which is 0, minus -1 times -2. So this is 2. It's not 0. If the determinant is not equal to 0, your matrix is invertible, which means you can compute an inverse for A. So in that case, like let's denote A, the matrix. Sorry, my pen doesn't work anymore. A, B, C, and D. So A is invertible if and only if A times D minus B times C is not equal to 0. Then this is called the determinant of A and denoted that of A. Now, something very interesting happens when you have a square matrix like that of order 2. Like if the determinant of A is not equal to 0, which means if A is invertible, then you can get an easy formula for the inverse. It will be 1 over determinant of A times. So you will commute these two coefficients, put D here and A here. And here you'll take the opposite of these ones, minus C and minus B. This is the inverse of the matrix A. So you can compute it by hand when the size of the matrix is a square matrix of order 2. Now, another phenomenon a matrix can represent is parallel equations. So for example, when you have a system of equations like that, like x plus y. So I'm writing 3 parallel equations with 3 variables, x, y, and z. So this is a system, minus 2z. So this set of parallel equations has some coefficients here, the coefficients of x, the coefficients of y, the coefficients of z, and it's equal to something you could call a column vector or a column matrix. And I can write this system like that. 1, 2, 4, 1, minus 3, minus 1. I'm taking the coefficients here. 1, 5, minus 2, times the column, the matrix. It will be a row matrix, X, but you can write it as a row matrix or as a column matrix. It doesn't make a difference. X, Y, Z, and it will be equal to the column matrix 2, 0, 1. This matrix will very often be called A. This one will be called X, and this one will be called B. The reason why checking that a matrix is invertible and knowing how to compute its inverse is very important is to solve parallel equations like that. Because if A times X is equal to B, then I can multiply if A is invertible, which means I have computed the determinant of A. If it's not 2 times 2 matrix, if it's not a matrix, a square matrix of order 2, you compute the determinant with your calculator. If the determinant of A is not equal to 0, it means A is invertible and the inverse of A exists. So A can multiply, but by the inverse of A on the left. Yes, I'm sorry, I'm confused between right and left. So this is on the left. So this is equal to identity, which means identity times X is X. Of course, the identity matrix plays the role of 1 in numbers multiplication. And then you have your solution, because this is going to be X, Y, Z. And if you can compute this, you'll get the values for X, Y, and Z. And you can compute this on your calculator if it's not of order 2. If it's of order 2, please try to do it by hand. So this is a very efficient way to solve parallel equations, okay? So this is the first application of matrices, and we'll see next time other ways to, other contexts in which matrices are useful for you.